Hey, this is Mr. Mitchell with another video. Today we're going to be talking about interpreting results as they have to do with scientific experiments. Interpreting the results of a scientific observation, well, they can be trickier than you might realize. The first obstacle to having accurate and good interpretation of your results is, well, precision and accuracy and, well, knowing the difference between the two. And hopefully, in all the experiments that you are part of, you will have lots of precision and lots of accuracy, but in the real world of science, it doesn't always work that way. So let's see what the difference is between the two. Precision is the exactness and consistency of measurements. You can see I got this information right here from a different text, and they say the degree of exactness in a measurement. So how exact something is precision. Now, it doesn't necessarily have to be accurate to be precise. Accuracy is how right something is. But let's talk a little bit more about what it means to be precise, to have precision. If you have precision, the measurements you get repeat each other. For example, if you are testing to see how many different species of birds come to a bird feeder under different conditions. If you have one day 23 birds come, the next day 24 birds come, the next day 23 birds again come, that's pretty precise. You're getting an exactness of measurement with that, as opposed to if you had a big discrepancy between the numbers for every day in which you repeated that experiment. So scientists hope for having precision in their measurements, and they also hope to have accuracy. Now, accuracy I kind of referred to earlier is how accurate something is, whether it is right. Accuracy refers to the difference between a measurement and its actual value, and you can see what I found in another text is as it approaches the standard or true value. In other words, how right it is. If you can be very precise but not right, not accurate. So if you have precision but not accuracy, there may be some kind of fault in your the data in which you are gathering, what you're gathering it with, maybe the instruments you're gathering it with, and actually you're hopefully going to get things right with what instruments you use to gather things. So if I have a nail here, ooh, it's going to be awful hard to draw a nail. Let's say I have a nail that is about this long. And I knew I should have stopped right there. But anyway, it comes to about right here. You could say, oh, that nail is maybe 2.6 centimeters, but it would be more accurate. It would be more precise, I would say, unlike this line. Boy, this line is not precise at all. It would be more precise to read it from the millimeter side. So you would put the nail down here and read it from the millimeter side, and you would know that it is 25 or 26 millimeters, however far it goes, instead of estimating how far it is between 2 and 3, because you do want to have precision. You do want to have accurate records. You do want to have precision whenever you have any kind of scientific experiment. Oh, I'm at school, pardon the bell here. But that's exactly what you're wanting, is more precision, so you would have the smaller unit as opposed to the larger unit that you would use this in. Oh, let's see. Let me look at my notes and see what I have next. Those people who thought that the sun revolved around the earth probably could take very precise measurements. They probably looked up in the sky in the morning, recorded exactly what the angle was that the sun was there, noticed it was later in the sky, later on in the day, and all the way nearly past nearly to the horizon at the evening, and probably could get very precise records. But as you know, they just were not right. They were not accurate whenever they had the hypothesis that it's the sun revolving around the earth, when it is not that case. It is the earth that is doing the revolving around the sun. So maybe that can be some kind of a easy way to remember. Here, what might be a good one. Say you're shooting targets at a bullseye. Here you have targets all over the place. It's not very accurate. Remember, accurate is right on the money. And you're wanting to, if you have accuracy, it's right around the bullseye here. And this does not have much accuracy. And it doesn't have much precision because all three of these shots are nowhere near each other. If it were precise, if it had a lot of precision, they would be bunched together, kind of like they are here. Now, these three shots, they were very precise, which means they were close to each other. However, you can see they're not accurate. I mean, they did not hit the bullseye. In fact, they were a long way from the bullseye. Here you have a high amount of accuracy. They're right around the bullseye, but they're around the bullseye in different directions, so it's not as precise as it is accurate. But of course, here's what you have, the best of both worlds. This is accurate, right on the bullseye, and precise all together. There are some other challenges in interpreting results. One challenge is the desire not to do much repetition. Many times people will want to make their conclusions based upon just one or two repeats of the scientific experiment, and they think, oh, that must be true, my hypothesis, and then they stop. No, 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 no. If you are really doing a scientific experiment, you're going to repeat it, repeat it, repeat it, and repeat it. If you are looking different days to see what species come to the bird feeder depending on what kind of food you have, you're not just going to make your conclusions after 1 day, 2 days, 3 days, 5 days. It's going to be a very long set of days in which you're going to record your data. You're going to end up needing to have something that is reproducible. Who knows? You might have just happened to have started your experiment during the migrating season, and 5 months from then you would have had hardly any birds there, and that plays an effect into what is actually true as far as what species come depending upon what. So you want to resist the temptation to draw your conclusions before you make a lot of repetition. Another challenge to interpreting results is going to keep accurate records. You definitely want to keep accurate records, and one of the big limitations to that is people assume that their hypothesis is correct. So once they see things, like say they see these bluebirds end up coming toward the pumpkin seeds when the pumpkin seeds are in here, they assume, oh, it's exactly what I thought it would be, and they don't keep accurate records. You need to keep accurate records. For example, when the blue jays came, what other factors were there, that you're repeating that. You really need to not just assume that your hypothesis is correct. You need to keep accurate records whenever you're having something like this. Checking out my notes to see where I am. Sometimes you have something like this. This is a graduated cylinder is what this is called. It has water in it, and it measures centimeters cubed. And over here you have a graduated cylinder which has some pennies in it. You might not can see it very well from there, but it's a group of pennies. And one way you can tell how much volume a group of pennies, or really anything, has is to drop it in liquid and see what the difference is between the water level before and the water level after. If you have here, it looks like a difference of, oh, what is that, maybe 84 or so, but still that's not very precise because I'm estimating here. But if you have one trial where it's 84 and another trial with different set of pennies that is 87, for example, something's wrong here. If you have the same number of pennies in both cases, you're going to have to look toward other factors. For example, there may be some bubbles that have been attached to the pennies that just kind of seem to stick to it. That would affect the displacement. Also, pennies made after 1982, I believe, have a different density than other pennies. So you would have to start checking the dates or maybe even the wear of the pennies. So sometimes factors that you might not expect would end up interfering with getting good, accurate results. And it could help you with the precision of your results too. If you're getting different levels with repeating the experiment with different pennies, it's not as precise as it should be. It should be the same every single time. Okay, your book is going to have a term called experimental bias. Now, experimental bias in your book is going to say some kind of problem with the equipment you are using, for example, would be experimental bias. Maybe there's a measuring stick, a metal measuring stick, which is bent slightly. And the fact that it is bent would mean it'd have a different reading than a measuring stick that would be straight. Say you had some scales which had some dust on it or some kind of debris on it, for whatever reason was not weighing as it normally would. That's what the book is going to call experimental bias. However, whenever you start looking experimental bias up in other places besides the book, they're going to include just normal old bias in the term experimental bias. Now, here's a pretty good cartoon to show you what normal bias is. Say this experimenter wanted to try to prove a hypothesis, but this one petri dish, the results weren't exactly what he thought they would be, and he really just kind of didn't want to use the results there. That's unprofessional, and that is biased. He is wanting a certain result to happen, and since he's wanting that certain result to happen, he's just going to kick out or throw away anything that doesn't give him the result he's wanting. And you know, we humans are like that. We kind of keep pressing on until we get what we want, and sometimes biased researchers are like that too. They think if this is true, then I can make millions of dollars on the market by selling whatever product it is. But they would just ignore, or hope the scientific community ignores, what the experiments actually show up as. So you definitely want to try to avoid bias. Scientists often use things like scatter plots, circle graphs, line graphs, and bar graphs whenever they show their results, and that's a pretty good idea. It's really a good idea to be able to have visuals to help people understand things. For example, here you have the diagram, the scatter plot of comparing arm strength with grip strength. So if you have a high comparison of both, then somebody who is strong in their arm will also be strong in their grip. And you can see that that kind of pretty much holds true. Wow, look at all the dots. That represents how many people that they used in that experiment to plot the arm strength and the grip strength. That's showing a whole lot of people. They didn't just pick 1 or 2 or 3 or even 5 or 10. They picked, oh gosh, that's got to be 60 or 100 right there. Line graph here. You can see it's plot on a graph, temperature per day. So on Monday, here was the average temperature. On Tuesday, here was the average temperature. Here was the low. Here was the high, and so on. That's a pretty good experiment. Circle graph looks like blood types of 25 donors. So they picked 25 donors and asked them their blood type, and had a pie chart. It's what they're often called, where it shows you kind of the percentages there. And here we have a bar graph. A bar graph that was a number of students and hours of television watched. And let's see what it says on the bottom here. I'm going to have to move this up some. Can't see the bottom X. Oh, this is the number of hours they watched. So you had number of students and the number of hours they watched. So most students watched between 9 and 11 or 12 and 14 hours. That must have been in a week. Now that would be something else if it were in a day. But anyway, just have one more thing on this particular video. Scientists should follow a code of ethics. Scientists must not perform actions that are a detriment to humans, a detriment to animals, or a detriment to the environment. In other words, scientists have to be nice in what they're doing. They can't run over people and take away people's rights and do things that are unethical. Hey, I've hoped you learn a little bit about interpreting results.